Thank you for your great writing. Appreciate it very much. I see where our thinking is strong and where it's weak, so I'll try to address those. We had some wonderings as well, so I'll try to talk about those because this is Algebra 2. Being able to understand the relationship between an equation and a graph. That's the main thing. And these graphs happen to have certain characteristics. That's where they get their names. Some people noticed that as well. So that's where I'll start off at. Exponential functions are named such because there's an x in the exponent. So that's where our variable, our input goes. If you want to put something in, you put it where the x is for a function. And that's what this notation says. I have an input and I get an output. Yep. So there's an input domain and an output range. And the name of the function depends on where the x lives, for sure, and what's happening with it. Okay, the reason why this is an exponential decay function is because our base is a fraction less than 1. That's why it's decay. If you have your notes from the growth sitting in front of you, you notice that it is the growth one was greater than 1. So connect the dots. So that's our job as mathematicians, is to connect the dots. Literally, right? The dots are the inputs and the outputs, and when we connect those dots, then we have ourselves this beautiful line that has certain characteristics. Okay, so we know we usually use the B color for what the base is going to be, and it's going to be a fraction. And we all love fractions. The reason why this is powerful is because when you multiply a fraction times itself, it gets smaller instead of growing. If I take 2 times 2 times 2, the result is a larger number. But if I take a half times a half times a half, you end up with an eighth. And that's a smaller. Would you rather have a half a cake or an eighth of a cake, right? So that's the uniqueness of an exponential decay function. It did not have a parent story on our 15 graphs. Somebody said, I wonder if there's more. Yes, there is. This is one of them that they did. It did not show up on our parent function that I had to write about last Friday. That's okay. Okay. Yeah, we're just going to adapt what we do know to this new idea. When things decay. Where would you see this? Someone said, oh, I'll never see these in the real world. Well, if you had any kind of science, did you guys play the bouncing ball science where you had to measure how high up the ball went every time? Did you ever play that game in science? You never had to do that yet? Maybe it's coming in physics. Anyway, it's one of those laws that there's a relationship between the prior bounce and the next bounce. And in pure mathematics, where nothing else is being acted on it, such as gravity, that ball literally will never stop bouncing. It just will bounce a portion of the height that it bounced before. You feel that? Can you feel that? There's no gravity. I start bouncing a ball, and the carpet's an issue too. See, it only goes up as much. Like that first drop, it didn't even come up halfway. It depends on the material of the ball. Yada, 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 yada. All those factors play in the game. But what I just did created a function, a decay function, because it went less every time. So it's a great application of what we're drawing here. We might watch germs in a petri dish, and we apply penicillin or some other substance and watch that, the number of, viral parts decay. Okay? So this is practical information. And you're going, no, I'm going to be a barista. What does this matter to me? Well, it might be profits. If after they hire you and they see the profits decay, they say, whoo, what's going on here, So just teasing. Anyway, See what I mean? It's all about the real world, for sure. That's where this stuff comes from. Back to the abstract. We got to watch the numbers happen. And what happens on a decay function, like I mentioned, there is a point of no return where it will never reach 0. This is if you have a parent function. But if you do anything to this parent function, like add a value to its equation, then that asymptote, that it's funnily called, will either go up above the x-axis or it'll go down below the x-axis, depending on the value of k, just like all the other graphs. It wasn't the asymptote that moved, it was the vertex that moved. It wasn't the vertex that moved, it was the y-intercept that moved. Yeah, everything, something moved when you added a k. Right, we've got this multiplier here. That will vertically stretch it. It shows up in the reference point. And bless you. The reference point for it, they gave us 2 so we could draw the graph of an exponential growth function. I'm only going to explicitly use 1, because I'm not going to have you draw a graph. I'm just going to have you find a graph. Okay, so this is true. This is another reference point, but this first reference point is the one that we are going to use for our graph exploration. Okay, so that's when you just take the multiplier. If you put in the h value, if I take h minus h, I get 0. And we want that. We want to keep it simple. If my exponent is 0, that b to the 0 turns into the factor of 1. 1 times a is a. That's why you take a plus k. Now, and when I was in your shoes, I'd sit in your seat. I didn't care why it was a plus k. But just for the good of the cause, if this b factor goes to 1, then you see why it's just a plus k? That if that, whatever that fraction is, to the power of 0 is not 1. Because 1 is the factor of everything. So then 1 times a is a plus k is the game you play to find a reference point. Okay? So where does that show up on the graph, right? Where does that reference point, which one am I talking about? And if you notice over here, I just have to circle it because there's not really a color for it. Okay, right here is the reference point. H is 0. That's good. That's good. We just don't know what, you know, a plus k is over here, so I can't color over here. But this is the reference point. We are in the parent graph. This is the one we're going to be looking for in the transformed graph. Now, if you want to, you can use a second point. But it's quite the gymnastics with the numbers. Bless you. So whatever this base is, you have to take the reciprocal of. That ends up being this point over here. And then you have to take your original or your transformed h, take away 1 because we want to back it up to where it's larger. Then we take a divided by your base, and then you add k to it. So that's a lot. It's a lot, you know. If you're a calculator wizard, no problem. The growth wasn't such a big deal because all you had to do was multiply. That was no big deal, I thought. But since this is a fraction to begin with, then you have to flip it, and then you have to divide it, and it's not worth the trouble. Okay, at this point in time, I just want you to know you can find a reference point by taking the h value from the exponent and that's the input, and the output ends up being a plus k. So you really don't even have to memorize it. You just remember, if I make this guy 0, it's 3 plus 4 is my other number. So h is 2, and then k is 7. Just throwing that out there. That's where they get this. So, okay, just example. Now, for whatever reason, I guess it kind of affirms our need to understand parent functions. They want you to take the function they give you and rewrite it back to it hasn't been transformed yet. Let me zoom that out a little bit, if I can, without whacking it completely out. One more. There we go. And so this is vocabulary. And I noticed that people said they didn't know what a parent function was, but maybe they knew, they just didn't know that's what it was called. So it's kind of an important thing here. Where did they get the parent function? Well, let's analyze this story here. Remember, this is A, this is B, right? This is H, and this is K. Just like the alphabet in order. So our original function, our parent function, what I see is that they have the base of their transformed function, and they just made it to the power of x. Nothing changed about x. Nothing changed about the exponent. That creates the parent function. Now, I don't know if you knew this. I didn't remember it till I got ready for this lesson. This value is called the decay factor. And that is the blue number, B number, the number in the power, the base, decay factor. So we didn't explicitly say that, but on our lesson before, that number in the exponential, can't find the thing when I need it, is a growth factor. There it is. Okay. This guy right here, he'd be the growth factor. That B would be the growth factor because he's larger than 1. This is the decay factor because you're taking a fifth of you instead of doubling you or whatever. Okay. Decay, the asymptote is from the shift up or down. This graph will never be 4. There is no number I can put in the exponent to make that 0. Nothing, nothing, nothing. It can get pretty small, but it'll never reach 4. And we've got our 3 parts here. Our H part is used in the reference point. H comes from the exponent. That's where they get the 2. A comes from the multiplier. Hopefully that's oh, I remember what that does. That vertically stretches it, right? And then K is the left and right. And again, we're not going to bother with the second reference point. It's nice to know you can, and you can look and find out. But my experience when I did the 10 homeworks, you only needed 1 reference point to find the right graph. Okay? You get that done, I would be happy as a clam. However happy they are, right? So parts are parts. You got it. There's one thing they didn't mention. That's the domain and range. On this worksheet, nothing is perfect, so I'm going to have to bring that into play. I'll use this example, and then I will do one other one down here below for an example about the domain and range hopefully by looking at the graph, you see any x can go. You see how that goes to the left forever and it's going to the right forever? So for our domain, in all of our homeworks and our assessments and our experiences with exponential functions are the set of all x, because those are the input values. Negative infinity is less than x, which is less than positive infinity. That does not change. No matter what's being transformed about the parent function, unless there's like a story that I only want positive x's or whatever, then it's all real numbers. The range, unfortunately, we didn't have it in these 13.1. They didn't like give you an opportunity to think, well, what if I reflect the graph? What would the range be? They didn't give you any of those options, but in this lesson they do. Yay. So the range. This is when my multiplier is positive. Okay, my multiplier out front here has to be positive. My range is the set of all y such that y is greater than k, because it's the asymptote. So you notice how this curve is above the asymptote? That's because our multiplier was a positive number. They didn't reflect it. Okay, so that's kind of a big deal for the homework. You'll be able to know what the range is. Then when we have an example where the range is negative, or the a is negative, I'll tell you what to do then. Okay, notice positive a greater than k. Okay, let's do. I think this is a great example. Why don't we jump down to number 4? That's a good example of what happens when the multiplier in front is negative. So we got to find our parts. For me, that helps first. If I don't do that first, I make mistakes, which I did earlier. I won't make, fool me once, shame on me. I do it twice, shame on me. Okay, here we go. Number 4. Let me zoom in. You see what I'm doing? And so you can do it too. And think about it. See if you can name those parts. See if you match my ideas. Okay, I'm not going to color. I'm just going to write their values. A is a -1. There's no number in front. There's a negative. The multiplier is a -1. B is 1/4. H is 6. Look crazy up here. And K is -5. We'll scoot over here. My original function is just that 1/4 to the x power. That's all I got. B to the x, just like it has above there. My decay factor is b equals 1/4. That's the base of the exponential function. My asymptote is y equals a -5. And my reference point. So I put H, and then I add A and K. It's simple as that, guys. -1 plus -5 is -6. Okay, if you weren't watching, you didn't see. This is A plus K, right? Look up there in the story above here. This guy right here. I just use this formula. because that's what happens. If I put a 6 in here, that goes to 0. 1/4 to the 0 power is 1. So that's where I got -1 minus 5. Right there. So that's the hardest thing to do, right? The rest are in your face. You got the rest. You know where to look. Like, where's your elbow? Where's your knee? Right? Okay, we want to talk about the domain and range because the homework's going to ask us to do that for number 4. The domain are all reals, and you'll have to do set notation, but that's okay. I'll just get a shortcut. Okay, range. Okay. Since A is less than 0, and they won't have you do this. I'm telling you why I'm changing the inequality sign. The set of all y such that y is going to be less than k. So what does that look like on a graph? Here's my asymptote. Okay, according to this, if I go 6 over and -6 down right there, my curve's going to get close to -5, but it will not hit -5. Okay? Then it goes down to the left forever, but this guy just, you know, never, in pure mathematics, it will never intersect the line y equals -5. I get it. So it looks a little more dramatic there. Okay. This is my asymptote. That is my orange line there. You do want to note that. And you just get to pick it, but that's what it looks like when A is less than 0. And the multiplier out front is less than 0. I think with your example and with this, what happens when there's things negative, I think you're ready for the homework. So if you want to get to your iPad, we can start the conversation and finish it tomorrow and have a work day. Okay, everybody got that number? This is all number 4. We didn't do number 6. Sorry. I think you'll be okay though. The others are so simple. 4 was probably the most challenging with that negative in front and the negative and that like that. Just remember to flip the sign, you know, on H. Okay, this is what your homework's going to look like. Am I in the screen? No, I'm too far big. There we go. Things are going downhill. Let me zoom out. Again. We'll just do like the first 3. Exponential decay functions. That's what they are. We put in a number, x, and we get out a value. So the larger the x, the smaller the value. Because I'm making smaller fractions. So what they're gonna have it just scripted for you. The transformation is a vertical translation. They'll even have the word up, and all you have to do is put in what makes the function go up, the k number, right? Then they'll have the domain all set up for you. They'll have all this, and you get to put in the negative infinity goes first. They'll have the less than signs there for you, and then you put in the positive infinity. It's like the number line. Negatives to positives. And the range, they have the set of all y such that they have the greater than sign there for you. All you have to do is say, where do I get the range from? Oh yeah, K. K transformed it, and K made the range change. Now, why didn't they say left or right? Because there's nothing being subtracted from X. That's all that happened. So put your number in, not mine. Okay. Whatever goes up, hopefully yours is up as well. They give us a transform function. Our brain is enjoying the game with the fractions and the exponents. They have all the story there. Only thing you have to put in is how far does it go left? And it's left because crazy X. This guy is the H number. Then it has the domain. Make sure you grab carefully. Your iPad treats you nicely. Right. My little shorthand here. And the range. Okay, this is a challenge. So it'll X such that Y is greater than. Okay, we're here on number 2. What's being added out to the side that you do not see? 0, A plus. So that's what stops the range. The range can't get any, it has to be after 0. So if I graph this guy, I just take my H and move it to the left 2. And then it still has the same asymptote as the parent function. And feel free to just graph them for fun. See what they look like. What happens when I do this? See, this was 1/3. This one's 1/10. That means it gets small really fast. 1/10 of you, a 1/10 of you, versus a 1/3 of you, a 1/3 of you, a 1/3 of you kind of thought. A 1/3 of a 1/3 of a 1/3. Last one, I'll let you to your own studies. We have a function that has been transformed. A, B, H, and K. Got to tell the story. You don't even have to say it was reflected. But this is where they get the statement reflected across the x-axis. Because it made all the positive values turn negative. Made all the positive outputs become negative. That's why it flips over the x. So you don't have to type anything for that, but it does say write 9. You have to put in your H and up 3, that's your K number. So H and K alphabetically. Okay? I'll be done with you. I'll turn off the video, get it started to upload, and you guys can keep on going on your homework. I don't think you'll run into any trouble maybe until you hit picking your graph. We can look all those over tomorrow, but maybe you got this thing. That would be great.